Okay, so this is 4.5 exponential growth video lesson. Okay, we start out with the equation y equals c e to the power of kt, and we have everything explained here, what c, y, k, and t are. This should look familiar. It's actually very similar to this formula right here, a equals p e to the rt. This is what we use for continuously compounding interest in banking problems, and in fact this formula stems from the main exponential growth formula, which is y equals c e to the kt. Okay, very similar meanings. Here instead of r in interest rate we have a k, but t is still time, although it could be another independent variable. We used to have p, which is our principal value. Now we have c, which is the initial value, and then y and a are both our ending or current value. Okay, so note this bolded statement here. Final answers must be accurate to 3 decimal places. Do not round before your final answer. So we're going to have to do some storing or using of the answer. All right, on this first problem it says Oliver Sudden is driving along a straight level highway at 64 kilometers per hour when his car runs out of gas. So here is his initial value. I'm going to label that as C. It says as he slows down, his speed decreases exponentially. So this is an exponential growth, or it can be a decay problem, with the number of seconds since he ran out of gas dropping to, and then they give us 2 other pieces of information, a current or ending value, a y, and then for that specific time. Okay, and so we're going to use this piece of information with the beginning value to solve for k, and we really need to do that before we even get to part A. All right, so I'm going to plug in my ending value, which is 48, equals 64 my beginning value, e to the power of k. I don't know what k is yet, but if I let 48 be my ending value, then my time is going to be 10. And you may notice that we kind of have a units issue here with seconds and per hour, but that's okay as long as we know that time is in seconds and the y and the c are both in kilometers per hour. As long as we stay consistent, we'll be fine. Now this is an exponential equation, and we can solve this using all the same strategies we solved any other exponential problem. Okay, first I'm going to divide by 64. All right, so this is going to become 48 over 64 equals e to the power of 10k. And now I can take natural log of both sides. Now when you take natural log of both sides, that's going to give you natural log of 48 over 64 equals, when I take natural log of the right side, everything will simplify down to 10k. So I'm going to go ahead and write that, 10k. Okay, and then the last thing I would want to do is divide by this 10. Now this is pretty much how it's always going to work out to find k. All right, you're going to do natural log of the ending value divided by the beginning value, and then all of that divided by your time, which in this case was 10. All right, now let's go ahead and go into our calculator. If you pause the video and get your calculator out if you haven't yet, because we definitely want to all be on the same track here. So we're going to do natural log of 48 divided by 64, close the parentheses, then divide by 10, and that gives us our k value. The next thing we want to do is to store this in for k. Now we've stored values before. You just hit the store button and then alpha whatever letter you want. Now I'm going to choose k since that's what we're writing down. It'll make it really easy to remember. Okay, so you can write your k value down, but if I use the k value anymore, I definitely want to use this decimal that's stored, not the rounded decimal. So we're going to go ahead and write down what our k value is, negative 0.0288, but I'm not going to use the rounded decimal. Okay, so now let's switch to our answers. So now we can go ahead and write our equation. We're not going to write 48 in the place of y anymore, okay, because I used the 48 and the 10, and once you use it to find k, you don't go back to that. We're going to write an equation that will work in the general, all right? So y equals, my initial value is always going to be 64, so I do include that, e to the power of negative 0.0288 t, and t is my independent value. Now again, when we use this, we're actually going to use the alpha k, not that rounded number. Okay, so this says predict Oliver's speed after 25 seconds. So they're saying when t equals 25, what is the y value? Well, we're going to get this by just plugging in 25. So we need to do 64e to the power of k times 25. We're going to do this in our calculator. 64, and then use the e button down here, 25k. And notice that there are parentheses here after the e caret, and that's important. And I get 31.177. So we do need to round these answers, but this answer is accurate to 3 decimal places. I didn't round and then round again. Okay, make sure you're using the same units that they used in the problem. And then for part C, this is giving us a y value. They're saying when y is 10, what's t? Well, this is going to require just a little bit of work. Let me go ahead and write down what we have. And I'm going to use k here, knowing that k is that stored value. Okay, so we could do we could use the calculator for this, doing a y1 and a y2 and finding the intersection. That would work, although you'd have to set the window manually. Or we can do the algebraic steps here that we did in the original problem, and I'm going to stick with that. You should be really good at these algebraic steps by now. So first thing is, I would divide by 64, and that's going to equal e to the power of kt. And then I'm going to take natural log of both sides. So then the natural log of 10 over 64 is going to be equal to the power of kt. Now remember, we're solving for t now. So then I'm just going to divide both sides by k. And so that's how we're going to find the value of t. So we do this in our calculator. Natural log of 10 over 64 divided by k. And that, oh, do you see my mistake? This happens from time to time. I did not close these parentheses. That's good for you guys to see it, because it's important. You know, it's good for you to see mistakes. You learn from mistakes. All right, 64.526, and the units on that are seconds in this problem. Okay, now really any other exponential problem can be solved this way, starting with this main equation. Okay, so on this problem, problem number 2, we kind of have a different scenario, but we're going to solve it a very similar way. It says the pressure of the air in the Earth's atmosphere decreases exponentially with altitude above the Earth's surface. So our pressure here, that's our dependent variable. That's going to be our y variable. Our altitude is going to be like time. It's going to be the independent variable. There is no time variable in this particular problem. So when they tell us that the pressure of the Earth's surface at the sea level is 14.7 pounds per square inch, that's going to be the initial value, the C. And then when they give us that the pressure is 2,000 feet, or the pressure at 2,000 feet is 13 psi, this is the information that we're going to use to find K. Okay, so let's think. Which of these two variables, 2,000 or 13.5, is the y value? Yeah, it's this one because it's pressure. And if you label your words with the variables, it makes it much easier. So we have 13.5 equals, the initial value was 14.7, e to the power of k times, not t, but altitude, so times 2,000. Okay, so again, we solve this by dividing by 14.7, so we have 13.5 divided by 14.7 equals e to the power of 2,000k. And then we take natural log of both sides. Natural log of 13.5 over 14.7 is equal to 2,000k. And then we would divide by 2,000. Okay, so our k value in this case, we go to our calculator and type this in. natural log of 13.5 divided by 14.7 and then divided by 2,000. And we get a really small number here. Okay, so you can write that number down if you want. You would have to use scientific notation. But this is a great example of why you want to store that number. The more specific or the smaller that number is, the more important it is to store in for k. Okay, so remember to store this number in for k. You hit the store key, alpha k. And you got to do that new every time. All right, now we get to the next part, and it says predict the pressure. Okay, so we're trying, well, I guess we should write down our equation next. This is going to be y is equal to 14.7 e to the power, and I'm just going to write k and not that number, t, knowing that k is this number. Okay, in part B, it says predict the pressure in, and they give you two different places, and they're giving you altitude. They're basically giving you the t value. So this is going to be 7,500. Well, what's the y value? This is the easier case where you're just plugging in 7,500 in for t. All right, so this is going to be 14.7 and then e to the power of k times 7,500. You get 10.68 psi, or 681. Okay, go ahead and try the next one on your own. If you feel like it's going to take you a few minutes, just pause the video. All right, and that was the answer to I. All right, if you haven't already done the second one, pause it and then give yourself some time to do it. But the answer should be 4.276. If you have questions on this second answer, then please ask your question in class tomorrow. All right, part C is the harder type of question, although it's really not that bad. They're giving you a new y value, so we write 0.9 equals 14.7 e to the power of kt, but we know how to solve this. First, we divide by 14.7, so 0.9 divided by 14.7 equals e to the power of kt. Then we're going to take natural log of both sides. So natural log of 0.9 over 14.7 equals kt, and then you're going to divide by k. Okay, so let's figure out what this t should be. And remember here, t is really altitude, so our units are going to be in feet. So we're going to plug this in, natural log of 0.9 divided by 14.7 divided by alpha k. All right, so here we get 65,607.749. And if you notice, I didn't really read that problem, I think because it makes me grossed out to think about it. I'm a little squeamish when it comes to stuff like that. Okay, let's look at the last problem we're going to do together. So this says an isotope of sodium has a half-life of 15 hours. Okay, so they're giving you T, and then they're going ahead and asking you a question. There's no step-by-step what to do. So let's first just write down the equation that we know works for all the problems. Y equals C e to the power of kt. So assume, we don't know how much we start with, but we know it's talking about half-life. So assume you start with 1 gram. Then after a half-life, you would have half a gram. That's the easiest scenario to assume. And then we know we're going to plug in T is 15 and know that our units are in hours. Some half-lives are years, some are seconds. You just have to know your units. Okay, another reason why I like starting with 1 gram is because then you really don't have to divide. You can go straight into natural log. So you take natural log of a half, and that equals 15k, and then your only other step is to divide by 15. So if you notice, it kind of works out the same way each time. If you if you want to memorize this, you can, but it's important that you know how it works. that way, if you forget the steps, you can just go through and do them. I know in chemistry you probably just memorized this formula, but now you know why it works. Okay, so here we get negative 0.046 2 for our K value, and this is specific to this element. It doesn't work for every element. All right, now we're looking at the next problem, and we're saying, well, how many hours, basically, what is the T value when your end amount is 40%? So let's assume we start with 1 gram again. What would be the final amount? It would be 0.4 grams, 40%. It doesn't, if you want to say, well, what if you start with more than that? If you start with more than this, if your C value is more, 40%, it will just be 40% of that number, and when you divide, it will be the same. So you might as well do the easiest scenario. Okay, so then we take natural log of both sides. This is what I like about these problems, is we get to skip that dividing step. And then we're going to divide by, in this case, K, because that's the constant, and so that will give us our time. So natural log of 0.4 divided by K. And there you go. Oh, I know what my problem is. This answer looked a little weird. Did you see my mistake? And again, this is a good mistake for me to make, because it's one you might be likely to make. I didn't store my K value in for K. And I tend to do that a lot. But the good news is, if you check the reasonableness of your answer, you'll be able to catch those mistakes. That other answer was not reasonable. And I'm just going to bring back, I don't feel like typing it in, so I'm going to bring back this one. And there we go. 19.829 is a much more reasonable answer than that 21,000 number. And I know that because 40% is a lot like 50%, which is the half-life. So this really shouldn't be that different from the half-life itself. Okay, we're going to finish this tomorrow in class, so definitely bring your questions.